Okay, so let's continue. So in the previous class, we discussed the impedance and the admittance, and we discussed the parallel and series combination of impedances. And now we will continue this discussion, and we have the delta to Y transformation, delta to Y transformation. And as you remember from previous chapters, we already discussed this delta to Y transformations. But in that case, we had only resistances. In that case, we had only resistances. And resistances, as you know, are positive real numbers. So they are real numbers, they are positive real numbers. So when we applied these three formulas in order to convert delta to Y, or these three formulas in order to convert Y to delta, we use the real numbers. We use to multiply and divide and add real numbers. But in this case, the formulas are the same, but you need to deal with complex numbers, So for example, in these three formulas, you are finding Z1, Z2, Z3, which is here in blue. So the given original circuit is the delta 1, and we need to convert this delta into Y. So in order to find the Z1, you are multiplying the nearby impedances, ZC by ZB, and dividing by the sum of all three impedances. So at the top, we will have a multiplication of two complex numbers, and in the bottom, you will have an addition of three complex numbers. As you see that the bottom is the same for all three impedances, Z1, Z2, Z3, but the difference is the top. So if you want to find Z2, you need to multiply the nearby impedances, which are C and ZA. And if you want to find Z3, you need to multiply ZB by ZA, or ZA by ZB, it's the same. So this is the only difference, that in the past we dealt with real numbers, but now you are dealing with complex numbers. So this is why you need to be able to multiply complex numbers, so to have them in polar form, and you need to be able to add the complex numbers. So you need to have them in rectangular form. And the final operation is the division of the top by the bottom. So the bottom should be converted after adding in rectangular form, should be converted to polar form, so you can do the division operation. And here, as you see, we are calculating ZA, ZB, ZC, which are the delta impedances. So the given will be Y, Z1, Z2, Z3 are the given, and you are calculating the three impedances. And as you see that the top is the same, Z1 times Z2 plus Z2 times Z3 plus Z3 times Z1. So the top is the same for all impedances, and the difference is the bottom. So in order to find ZA, so ZA is surrounded by Z2 and Z3. So you need to divide by the Z1, the opposite one, which is Z1. In order to find ZC, for example, I need to divide by Z3. In order to find ZB, I need to divide by Z2. You need to divide by the opposite one. So here the top is to multiply the nearby ones. And here the bottom is to divide by the opposite one, not the nearby one. So these formulas were discussed when we discussed the combination of resistances. And as I told you, that the only difference is that here we are dealing with complex numbers, while in the previous we dealt with real positive real numbers. Any questions, please, on this slide? Okay. So here we have an interesting example, so you can solve this example. As you see here, we have Y. This is Y. You can convert it in delta. So if you convert this Y into delta, you will be able to solve this circuit, because as you see, this capacitor is not connected in parallel with this one, neither with this one. So we need to convert this y into delta. While once you convert this y into delta, you will have these three impedances. So one impedance will be in this form, and another impedance will be connected in this form, and the third impedance will be connected in this form. So as you see here, you will have this impedance in parallel with this impedance. This impedance will be in parallel with this impedance, and this impedance will be after you take this parallel, they will be in series, and then with this in parallel. So this is how you can convert the delta to Y connection. I will not give it as a homework, so I will give something else as a homework, but it is very interesting to do this example so you can train yourself how to multiply and divide by complex numbers, okay? And here we have source transformation and Thevenin Norton equivalent circuits. So again, what we applied on resistances can be applied on impedances. So impedances, Z are the complex numbers. So Z is the complex number of R plus J. And here we will have the inductive reactance minus the capacitive reactance, where the inductive reactance XL is equal to omega L, which is equal to 2 pi times the frequency times L. And the XC is equal 1 over omega C, which is 1 over 2 pi FC. So once you have the frequency given, once you have given the inductance in Henry or the capacitance in Farad, you can calculate the inductive reactance, you can calculate the capacitive reactance, and apply in these formulas. So for example, here we already have the capacitive reactance here. We already have the inductive reactance here. So you don't need to apply these two formulas because you already have XL and XC. So you need to apply the impedance in this way. And as you see here, we have a voltage source and impedance connected in series, and this is Thevenin equivalent, if you remember. So we can convert this combination of voltage source in series with a resistor or impedance. Now, starting from this point, we will see impedance. So it can be converted into current source in parallel with the same impedance. So as you see here, Z system, and here we have Z system, the same impedance. So the only question is how to find this value, the value of this current source. So the current source, I source, is equal to this given voltage source and divided by the impedance. So this is Ohm's law. If you want to do the other wise conversion, so you have given the current source and impedance in parallel, and you need to go back to have a voltage source and impedance in series. So the impedance is the same impedance, and here we need to find the value of the voltage. So the voltage source will be the product of this current source and this impedance. So again, we apply Ohm's law. So this is how to convert from a voltage source and impedance in series to current source with an impedance in parallel, or vice versa, Any questions about source transformation, please? Is it clear, please?
Yes, Professor.
Okay. And here we have a Thevenin and Norton equivalent at the end of this slide. So as you remember, in Thevenin equivalent, any given circuit, any given linear circuit can be converted in a voltage source, which is equal to V Thevenin, or V open circuit between these 2 points, A and B, in series with the Z Thevenin. And let me remind you how to find V Thevenin. V Thevenin can be found by finding or calculating the voltage source between A and B. So it's the open circuit voltage between these 2 points. And how to find Z Thevenin? So you need to deactivate all sources. And after deactivating all sources, you need to find the impedance while you lock to the circuit from this point between A and B. So you need to find the impedance with according or with respect to the points A and B. So this will be the equivalent in the Thevenin equivalent. So what was applied to a resistive circuit will be applied here, but you need to deal with impedances. Same thing for Norton equivalent. So the difference between Thevenin equivalent and Norton equivalent is that Norton used current source in parallel with an impedance, while Thevenin used voltage source in series with an impedance. So here we do the same. So in order to find I Norton, you need to short circuit the points A and B, and to find I short circuit. So you need to find the current which is flowing between these 2 points. So this will be I Norton. And how to find Z Norton? It is the same as Z Thevenin. So you need to deactivate the sources, open this link A and B, and you need to look at the circuit from this point and to find the impedance between A and B, or with respect to points A and B. And it should be the same Thevenin impedance. So impedance in Norton equivalent and the impedance in Thevenin equivalent are equal or are the same, and this can be also understood from the source transformation. Any questions on this slide, please? Okay, so in order to make sure that we understand this topic, so let's say solve one example. So we need to find V node. So this is, as you see, V node between these 2 points. So here we have the positive polarity, here we have the negative polarity. So this is V node, and we need to find it. And we need to find this voltage using source transformation technique. So we need to simplify the circuit by finding the source transformation technique. And as you see from this circuit, we can find this voltage if we know the current which is flowing in this branch. Because if you know this current, let me write I node. If I can know I node, which is flowing in this branch, so I will multiply I node by the impedance, which is 10 minus J19. So this will be the impedance. If I multiply I node by this impedance, it will be V node. It will be V node. So the first thing, I need to find this current. And as you see that this current or this voltage source will give current in this direction, and the current will flow this and up to this point, and then it will split into 2 parts. One part will go downward and back home, and the other part, which will be I node, will go with this direction and back home. So as you see that I have 2 currents, so I need to use either nodal analysis to find the voltage here, or I can use mesh currents or whatever else. So in order to understand today's topic, so we will use voltage source transformation. And as you see here, the first transformation that can be done is this voltage source in series with the impedance. So this voltage source, let me redraw it in another way, so to make sure that we do understand the topic. So here we have this resistor and this capacitor, and this Z will be, I will write Z equal to 1 because the resistor is equal to 1 plus J3 ohm. So this is J3 ohm. So this is the impedance. So this is Z, the impedance, as you see from this branch. And this is the voltage source, which is given as 40 into 0 angle. So now I want to convert this into current source with the same impedance. As you see, the impedance is the same, 1 ohm and 3 ohm as inductive reactance. So here we have 1 ohm resistance, and here is the inductive reactance J3 ohm. As you see, the same impedance. We are not changing the impedance. So now the idea here is to find the current value, the current source value. And according to the source transformation, we need to divide the voltage source by the impedance. So here we are doing that. The current is equal to the voltage source, which is 40 into angle 0, divided by the impedance, which is 1 plus J3. 1 plus J3. And this is the division results. So in order to get rid of the complex number in the bottom, I believe that you know that you can multiply by the conjugate. So you can multiply by 1 minus J3 divided by 1 minus J3. And then the bottom will be the difference between squares, So it will be 1 square minus J3 square. This is the bottom will be. And 1 square is 1, 3 square is 9, J square is negative 1, so it will be negative 9. And this will be 1 plus 9, and this will be 10. This will be 10. So this is how to get rid of the complex number in the bottom. So you can multiply by the conjugate, or you can convert the bottom in polar form, and you divide the magnitude by the magnitude, and you deduct the lower angle from the upper angle. So it's up to you. So if you do the this division operation, we will have the current value as 4 minus J12 ampere. And here it is, 4 minus J12 ampere. So the first step that we did, that we changed this voltage source in series with impedance into current source with in parallel with the same impedance. Is it clear, please?
Yes.
Yes,
Any
sir.
more responses,
Thank you.
please? Okay. Only.
Yes.
Okay. Okay. So now the next step, as you see, let me remove this red circle. So the next step, as you see, that we have two parallel impedances connected in parallel with each other. So we have these two impedances connected in parallel. So one impedance is 1 plus J3 ohm. This is one impedance. The other impedance is, as you see, resistance 9 and the reactance negative J3. So the other one is 9 negative or minus 1 minus J3. So these are the two impedances that we have. So in order to have their parallel combination, so I need to multiply them by each other, and then I need to add them, divide the result by their addition, So I need to multiply. So the first one is 1 plus J3. The second one is negative, is 9 minus J3, 9 minus J3. And I need to divide by their addition. So their addition, you need to add the real part by the real part and the real part. So 1 plus 9, it will be 10. And then plus J3 minus J3, it will be 0. So you can, just for clarification, it will be plus or minus J0. So we don't have imaginary part. And here you need to multiply these two numbers. So either you convert them to polar form, or you multiply 1 by 9 and then 1 by negative J3, and then plus J3 multiplied by 9, and then J3 multiplied by negative J3. So either way, either ways are fine. And as you see, the result of the parallel combination is 1.8 plus J 2.4. So this is the result of this parallel combination. And again, we will have one combination, one result, which is RL result. This is in red. And as you see, I have a current source with this combination, so I can convert them to voltage source with the series in this combination. So here we have this combination. It is now connected in series. And now I need to find the voltage source value. If I go to the source transformation, the voltage source value will be the impedance multiplied by the current source. So here I have the current source 4 minus J12. And here I have the equivalent impedance, which is 1.8 plus J2.4 ohms. So if I multiply them by each other, I will have the value of this voltage source. And as you see, the value is 36 minus J12 volt. So this will be the voltage source. Now I arrive to a single loop circuit, as you see. So the current here, I0, it will be the same current here. So I can find it by applying KVL to this loop, by applying to KVL to this loop, or by dividing the voltage by the sum of all impedances. And in order to do the sum of all impedances, because they all are connected in series, again, you need to add the real parts alone. So 1.8 plus 0.2, it will be 2, plus 10, it will be 12. So the real part is 12. The real part is 12. Now you need to add the imaginary part. So 2.4 plus 0.6, it will be 3. Minus J19, it will be J16. So minus J16. So this is the total impedance in this circuit. If you divide the voltage, which is 36 minus J12, over the total impedance, this will give you the current that we are looking for. The current that we are looking for. Any questions on this slide, please? Okay. So so this is how to find the current. So we have the total impedance, which is 36 divided by, this is the voltage, sorry, 36 minus J12 divided by the total impedance 12 minus J16. So 36 minus J12 divided by 12 minus J16. This is the same that we found in the previous slide. And here you can take 4 as a common factor, 4 in the bottom, 12 in the top. Then you can simplify the operation. So 12 divided by 4, it will be 3. Then you can divide these numbers. And then here is the final result, which is the current, Okay. So again, here you can multiply by 4 plus J4, 3 plus, so in order to get rid of the bottom, so you multiply by 3 plus J4 divided by 3 plus J4. So as you see, this is 1, so you can multiply anything by 1. So 12 divided by 4 is equal to 3. And in the bottom, we will have a difference between squares. So we will have 9, 3 square is 9, 4 square is 16. So 9 plus 16, it will be 25. It will be 25. So the bottom, the top, sorry, the bottom is 25. So you need to multiply the top. So you need to find its value. So again, you need to get trained how to calculate or how to make different operations on or with complex numbers. So this will be I0. So once we found I0, then I will multiply I0 by this impedance, and this will be V0, which is required. So V0 is equal to this current, 1.56 plus J 1.08 multiplied by the impedance, which is 10 J19. And this will be the voltage across this impedance, which is V0, which is required to be found in this circuit. Any questions, please? Okay, is it clear for everybody, please?
Yes, Professor.
Okay. So here we have examples. So please try to solve this one. So you need to find using technique source transformation. So as you see here, you have voltage source with impedance. Here you have voltage source with resistance. So you need to convert it to current source with the resistance in parallel. And this will be current source with a reactance in parallel. Then you will have four components which are in parallel, so you can find their equivalent. Okay, solve it. I will not give it as a homework, but it's very interesting to be solved. Okay. Okay, so let me switch to the next presentation. Okay. So in the previous presentation, we discussed the source transformation, Thevenin equivalent, Norton equivalent, using impedances, using frequency domain circuits or circuits given in frequency domain where we have inductances and capacitances. So you need to use impedances. And also this applies to the other techniques that we had, like the node voltage method and the mesh current method and all techniques and even superposition method. So here we have one example about the node voltage method. So as you see here, we have a circuit. In this circuit, we have 1, 2, 3, 4, 5, 6, 7 simple circuit elements. We have independent current source, the value of which is 10.6 into angle 0. We have resistance 10 ohm. We have resistance 1 ohm. We have inductive reactance J2 ohm. We have capacitive reactance negative J5 ohm. We have resistance 5 ohm, and we have dependent voltage source. And this voltage source is current controlled. Because as you see that in the X value, we have the controlling variable given as a current, which is Ix. So this voltage source is equal to 20 Ix volts, 20 Ix volts, because this is voltage source. And if you look in the circuit for Ix, so here we have Ix. So Ix is the current that is flowing between these two nodes, this node and this node. So this is Ix. So once, of course, you can solve this circuit using any technique that you want. But once we need to study node voltage method, so we will use the node voltage method. So the first thing that I need to do is to identify the nodes. So here we have a lower node. So we will have one node here, one lower node. We have here one node. We have between these two elements another node. Here we have one node as well, and here we have one node as well. So as you see that we have 1, 2, 3, 4, 5 nodes. So we have in this circuit 5 nodes. But as you remember from the node voltage methods, I need to look for the essential nodes. So an essential node is that node to which we have 3 or more simple circuit elements connected. So I see here one simple circuit element, another one, and a third one. So this node is essential. This node has only two simple circuit elements, this one and this one. So this node is not essential. This node has 3, 1, 2, 3. So this is essential. This node has only 2. So it is not essential. And the lower node has 1, 2, 3, 4 elements. So what I need to do now, I need to remove this node and this node because they are not essential node. And I will say that I have only 3 essential nodes. I have only 3 essential nodes. Okay, so I will have a number of equation which is equal to n essential minus 1, and this will be 3 minus 1, which is equal to 2. So I will have only 2 equations to solve, only 2 equations to solve. And again, after we identify the number of the essential nodes, you need to choose one node to be the reference. And if you still remember, I advised you to choose that node to which the largest number of elements are connected. So here we have 1, 2, 3, 4. So it is preferable to select this node to be the reference. Of course, you can select any other node, it's fine, but in order to minimize the number of calculations, so it is preferable to choose this node. After choosing the reference node, we assign the unknown voltages. So this node will be 1, this node will be 2, and the voltage plus minus V1, which is between the node 1 and the reference node, and the voltage V2 will be the voltage between node 2 and the reference node. So now we assigned all the voltages and non-voltages, and we see that we have 2 variables, V1 and V2. Then we need to apply KCL. So you need to apply KCL to node 1 and to apply KCL to node 2. This is how we use node voltage technique or a method. And KCL is also can be applied in frequency domain. So we applied this KCL in resistive circuits, in DC circuits, and it is also valid to be applied in frequency domain. So let's apply KCL to node number 1. So let's apply KCL to this node. So as you see, this current is flowing into the node, so it will be negative. So negative 10.6 into angle 0. So once the angle is 0, you can ignore it. You can ignore it. So it will be negative 10.6. Now I need to take this current and this current. So the current which is going down, it will be V1 divided by the impedance, and the impedance here is 10 ohms. So we have only resistance. So it will be V1 divided by 10. And now to see what is the current flowing from 1 to 2. So it will be V1 minus V2 and divided by the impedance. And the impedance here is 1 ohm plus J2 ohm. So V1 minus V2 over 1 ohm plus J2 ohm. And this is according to KCL is equal to 0. Is KCL to node 1 clear, please?
Yes.
Okay. Now let's write KCL to node 2. And again, I need to express the 3 currents related to node 2. So the current which is going downward, the current which is going away from the node. Here I don't have any current sources, so I will use Ohm's law, and I will start with this current that is going to this in this direction. So the current, this current will be the voltage difference, which is V2 minus V1 over the impedance in this branch. And here we have V2 minus V1, and the impedance in this branch is 1 plus J2 ohm. So it's 1 plus J2 ohm, okay? And now the current which is going downward, it will be V2 minus 0, which is the reference, minus 0 over the impedance, and the impedance here is only reactive element, which is negative J5. So it is V2 minus 0, so it's V2 over negative J5. And now we are doing this current, so this current will be V2 minus the potential in this point, and the potential in this point is 20Ix. The potential in this point is 20Ix. So it will be V2 minus 20Ix over the impedance in this branch, and we have it only 5 ohms. And this is equal to 0. As you see, this is KCL for the second node, essential node, and you see that we have V1 and V2 are the variables, and we still have Ix, another third variable. So we need to express Ix through V1 and V2 in order to eliminate the third variable. So Ix, if I look to the circuit, so here the circuit, here Ix, or here it is also Ix. So we see that Ix is equal to V1 minus V2 and divided by 1 plus J2. So Ix is V1 minus V2 and divided by 1 plus J2. Can I say that Ix equal to V2 minus V1 divided by 1 J2? Can I say that?
Say that again, sorry.
Can I say that Ix equal to V2 minus V1 over the impedance?
Yes.
But Armin says no. So who can tell me why I can or why I can't say that Ix equal to V2 minus V1? So according to Armin, because of the direction of the current Ix, thank you, Armin. So as you see, the given direction is from this point to this. So you need to be careful which direction is to use. So once the direction is given from here to here, then I need to say V1 minus V2 over the impedance. And here it is V1 minus V2 over the impedance. Otherwise is incorrect. Otherwise is incorrect. So you need to be careful, please. In the given circuit, what is the direction of the current? So as you see that the direction is from 1 to 2, so it will be V1 minus V2. Is it clear now, please?
Yes.
Okay.
Thank you.
Yeah. So as you see here, we have two equations where V1 and V2 are there. And of course, we can replace this Ix by its expression here. And then you will have two equations with two variables, which are V1 and V2. Solving these two equations, taking into account that all the coefficients here are complex number, then V1 will be as much and V2 will be as much. So this is the solution of these two equations, two algebraic equations with the complex numbers, After having the voltages, I can find all the currents. As you see, I need to find IA, IB, IC, and IX if required. So IA, as you see, the current flowing downward, so it will be V1 divided by 10. So Ix is V1 divided by 10, so this will be the value of it. And Ix can be calculated as V1 minus V2 divided by this impedance. So here it is. IB is the current flowing in this direction, so it will be V2 minus 20 Ix divided by 5, as you see here. And IC, the current which is flowing downward, this capacitor will be V2 divided by this reactance, and it will be as much. Any questions, please, on this example? Any questions on this example? So as you see, that same rules, same methodology that we used in order to solve the circuit with resistances using node voltage method. The only difference here is that you will have complex numbers as the coefficients. So you need to look at each branch. So here we have only one component, here we have one, here we have one, while here we have two, okay? Okay, so this is the next homework. So this is the next homework. I guess it's homework number 13. I will double check. I think it's homework number 13. So what we need to do is to use nodal voltage method to find the steady state expression of V of t. So as you see here, we have a voltage, this voltage, the same voltage which is across this resistor, across this capacitor, or across this inductor, because they are connected in. So you know the current in any of these components, multiply it by this component, or if you know this current, you multiply it by this component or this current. So what you need to make sure that first of all, you have the time domain expression. So you have I source is given as much and V source is given as much, and here is the frequency. So what you need to do first is to convert this circuit from time domain to frequency domain, So let me remind you how we convert it into frequency domain. So the current source here will be the magnitude into the angle, and the magnitude, as you see, is 10. I maximum is 10. The angle is 0. So this current source will be 10 into angle 0 amperes. And the voltage source at the other side of this circuit is 100 into sine omega t. And as you see here, we have sine. The first thing that you need to do is to convert it into cosine. And we can convert it into cosine by deducting 90 degrees. So the voltage source will be 100 into negative 90 degrees volts. So this is how we convert from time domain to frequency domain. The resistance will be the same. The capacitor will be equal to negative J 1 over omega C. So here, as you see, C is given as 9 into 10 to the power of negative 6, because microfarad. And omega is given as 50 kilo radian per second. So it is 50 thousandths. It is 50 thousandths, okay? So you can find the the capacitive reactance. And here you have 100 microhenry. And you know that in order to convert it to frequency domain, you need to multiply this 100 millihenry by omega, and omega is 50,000. So, and you put this value here and this value here. Then, and this 20 ohm will remain 20 ohm. So because it's a resistor, it will not change. Is it clear how we convert to frequency domain, please?
Yes.
Okay.
Yes, it is.
Okay, and this is 100 to the power of negative 90. It will be negative J 100 volt, negative J 100 volt, because negative 90 is negative J, plus 90 is J. Okay, so now we convert it to frequency domain. How many nodes we have? So in the chat box, it says 2 nodes.
Three no.
3 nodes. So we have 3 nodes. So we have 1 node here in the bottom, and we have 1 node here. And where is the third node?
Between the volt source and the resistor.
Yes, this is the third node. Is the third node essential node?
No.
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 So although we have 3 nodes, but we will consider only 2 nodes, right? So if you take the lower node as a reference, as you see, the lower node as a reference, so you need only to write KCL for the upper node. So V of t will be the same as V1, which is the unknown voltage. So you need to apply this current source going into, it will be -10, then V1 over 5, V1 over the capacitive reactance, V1 over the inductive reactance, and V1 minus J100 over the 20. And then you solve the equation for V1. If you find V1, this will be the same as the unknown V, the unknown V. But after you find V1 in complex number, you need to convert it into time domain, which is, as you see, the same frequency, 50,000 T, and this is the angle that you will have. So V1, according to this result, V1 will be equal to 31.62 into angle -71.57 degrees volts. So this is the solution of the equation of KCl to the upper limit. So this is how to solve this homework. So please do it. I will post it tonight also. And I already went through the steps. So you need to make sure that you have cosine function all the time. You need to make sure this is because if you, for example, if you don't take this into consideration and you will have it as 100 without this negative J, so of course the solution will be incorrect. The entire solution will be incorrect. So you need to be careful that you do it with a cosine reference function. Okay. And the current here, the mesh current method. So again here, any question please about the homework before starting the mesh current? Is the homework clear, please?
Yes, it is. Thank you.
Okay. Okay, so let's see the next method, which is the mesh current. The mesh current. Again, the mesh current, you know that you need to have a planar circuit, and in this example, we do have a planar circuit. We have one mesh and we have another mesh. We have 3 loops actually in this circuit. So the outer loop and the inner 2 loops. The inner 2 loops are meshes. The outer loop is not a mesh because the definition of the mesh is that a loop that doesn't contain another loop inside it. So the outer loop is not a mesh. So we have 3 loops, but we have 2 meshes. And you need to assign these 2 meshes in the clockwise direction. So I1, I2, you can assign them in the opposite direction, but let's go with the textbook, and with even other textbooks, always assign them to be in the clockwise direction. So here we have different voltages, we have different currents that we need to find after solving this circuit. So now we need to apply, after we identify the number of meshes that we have, and after we assign the mesh currents, I1 will flow in this mesh, I2 will flow in this mesh, we can write KVL to these 2 meshes. We need to write KVL. As you see here, we have a voltage source, independent voltage source, and we have dependent voltage source. And this dependent voltage source is also current controlled, as it was given in the previous example. And as you see here is IX. So whatever IX in this branch will be multiplied by 39, and this will be the voltage of this voltage source. Okay. So we need to write KVL for the first mesh. And let me remind you how we write KVL. So if you going into the direction of voltage rise, it will be negative voltage. If you going in the direction of voltage drop, it will be positive voltage. The voltage across the passive elements, we will take it as voltage drop. And the voltage in each element is the product of the current and that element. So it will be I1 times 1, I1 times J2, I1 minus I2 times 12, and so on. So let's go with, and we'll start with this voltage source. So if we go from bottom to the top, so you are going from negative sign to positive sign, and this is voltage rise. Voltage rise means that negative sign. So the first component will be negative 150, negative 150. But if we take negative 150 to the other side of the equation, it will be plus 150. So we need to write KVL and be equal to 0. If you take 150, the negative 150 to the other side of the equation, so it will be plus 150. Is it clear why 150 is positive here? Is it clear, please, why 150 is positive?
Yes.
Okay. So let me please, so I don't have time here. So what is the time? Let me see what is the time. Okay, so I want to double. Okay, okay, that's great. Okay, so here we have a negative 150 taken to the other side of the equation, so it will be plus. Now I want to see the voltage drop. So the voltage drop across this impedance will be the current I1 times 1 plus J2 ohm. And here it is, I1 times 1 plus J2 ohm. And the voltage drop across this impedance will be 12 minus J16, 12 minus J16 multiplied by which current? By I1 minus I2, because I2 is also flowing through this impedance in the opposite direction. So it is 12 minus J6, this is the impedance of the branch, times the current in this branch, which is I1 minus I2. So this will be KVL for the first mesh. Is it clear, please?
Yes, it is.
Yes, Professor.
Okay. Now let's write the for the second mesh, and we will start with the middle component here as well. So now we are writing with respect to I2. So I2, the voltage drop across this branch will be 12 minus J16. This is the impedance times the current I2 minus I1, because I1 is flowing in the opposite direction. So this is the first voltage drop, as you see. 12 minus J16, the impedance of the middle branch, times I2 minus I1. And plus, now I want to calculate the voltage drop across this branch. Across this branch here, we have only one current, which is I2 is flowing. So it will be I2 times this impedance, and this impedance is 1 plus J3. So it will be 1 plus J3 ohm times the current I2. And here, the last component, as you see, the voltage drop, we are going from the top to the bottom. So we are going from plus to minus, and from plus to minus is voltage drop. So it will be positive. So plus 39Ix. So plus 39Ix. So as you see, we have two equations, but we still have one third variable, Ix. If you go back and look at this circuit, given circuit, you will see that Ix is that current which is flowing downward in the middle branch. So if I want to express Ix through I1 and I2, so it will be I1 minus I2. Why I started with I1?
Because of the direction of the IX current.
Yes, exactly, because I1 is in the same direction as Ix. So it will be Ix equal to I1 minus I2 in given here in this equation. So if you replace Ix by its value, I1 minus I2, then you will have two equations, and these two equations with complex factors. If you solve these two equations, you will have I1 equal to this value, I2 equal to this value, and through them you can calculate Ix by this equation and to be this value. Now in this question, it is requested to find the voltages here indicated, V1, V2. So as you see, V1 is will be the product of the mesh current I1 times the impedance, this impedance. So it will be I1 times this impedance. So this is V1. V2 will be the product of I2 times this impedance. So V2 is the product. So what is V2? V3, this is, sorry. V2 will be the product of this impedance time the current flow downward, because here is the plus of V2, here is the negative of V2. So it will be times I1 minus I2, which is Ix. So here we have Ix. So this is V2. 12 minus J16 times Ix. So this is V2. And V3 will be this impedance multiplied by I2. So this is V3, I2 multiplied by 1 plus J3. So what will be the voltage, let's say V4, which is given in this polarity? So how we can find V4? So this is V4, this is the plus, this is the minus. I want to find V4 across this impedance.
Don't make the current negative.
Yes, so it will be 1 plus J3 ohm multiplied by, so I will add negative here, multiplied by I2. So simple. And as you see here, the given polarities, so it was given in the same direction as the current, and this is the current for I2. So you see I plus I minus. So you don't need to reverse the sign. But if I give you a voltage which has a polarity which is not in the same direction as the current, so of course you need to add negative sign. Okay. Any questions on this example, please? So here we have one example, so please solve it. We'll not give it as a homework, but as you see here, you have 3 meshes. Here we have 1 mesh, in the middle you have another mesh, and here you have a third mesh. The third mesh has a current source, so its value already known. So you need to write for the first mesh and the second mesh. You need to write the equations, and so you will have 2 equations with the 2 variables, and you need to find I this circuit. Okay. The last topic in this chapter is the transformer. So we have an equipment which is the transformer, and without the invention of the transformer, we will not have a wide use of electricity. So the transformer, main or the most important invention in electrical engineering, that allowed us to use the electricity and to be able to transmit electricity over thousands of miles. And the transformer, if I want to describe it in a simple way, is composed of 2 coils, and these 2 coils are magnetically coupled. And this is, as you see, the magnetic coupling M. And if you want to represent the magnetic coupling in frequency domain, it will be treated as you treat the inductance. So it will be J omega M. And here is the inductance of the first coil. Here is the inductance of the, or the inductive reactance of the second coil. The resistances of the wires of which these coils are made are R1 and R2. At one side, we have the system connected, the source with the system impedance, and the other side, we have the load connected. And this transformer is actually the last step of transformation before our houses and different factories. So the transformer is a device that changes AC electric power at one side. So here we have AC electric power to AC electric power at different voltage level, and it doesn't change the frequency. So we see the frequency here, omega, and the frequency here is omega. So as you see, we have here one loop, and here we have another loop. So we can use mesh analysis in order to solve this circuit. So here we have I1, the first mesh, and here we have I2, the second mesh. So we can write KVL for this two loops. So writing KVL for these two loops is the same as the previous example, plus one exception is that you need to take into account the mutual coupling. So the mutual coupling here is J omega M multiplied by the other current for the first loop. And in the second loop, it will be J omega M multiplied by the first current in the second loop equation. So, and as you see here, we have negative sign, negative sign. Why is that? Because the dot convention. If you still remember from the magnetically coupled circuit when we solved them. So as you see here, the current is entering the dotted terminal, while here the current is entering the undotted terminal. So the current is flowing in this direction. So the current is entering the undotted terminal, while the current here is entering the dotted terminal. So if we have this difference, so the sign will be negative. So here the sign is negative, and here is the sign is negative. So as you see, we have two equations with I1 and I2 unknowns, and they can be solved. So if you have ideal transformer, in ideal transformer, there are no losses, and there will be a magnetic coupling coefficient equal to 1. So as you remember, the magnetic coupling coefficient K or M is equal to the square root of L1, L2. So it is equal to 1. That means all the magnetic field lines from the first coil are intersecting the second coil, and all the magnetic field lines from the second coil are intersecting the first coil. So this is ideal case. It is not there in nature. So it's very hard to achieve, or it is impossible to achieve actually. And if we ignore all the resistances for all the wires, so we will say that self-inductance is infinity and the coils losses are negligible. So if we have these three points achieved, and it is impossible to achieve them, but we will consider that they are achieved. So then the ratio between the voltages V1 and V2 will be represented by the ratio of the number of turns. So N1 is the number of turns of the first coil, N2 is the number of turns of the second coil. And the currents also relationship in the first and secondary windings will be also given in using the number of turns. So if you know the number of turns, you consider ideal transformer, so you can know the relationship between V1 and V2 and I1 and I2. If the number of turns are the same, N1 is equal to N2. If N1 is equal to N2, then V1 is equal to V2. And we don't have any transformation. So in order to have transformation, you need to change the number of turns. If you want to raise the voltage, you need to have N2 more. If you want to decrease the voltage, you need to have N1 less. This topic will be explained very in details in EE 350. Okay. And the last slide here is the phasor diagram. So let me please again just double check the time. So the time, okay, that's great. We have plenty of time. Okay, so the last topic for today is the phasor diagram. So let's go through the text in order to define the phasor diagram, and then I will explain all these for you. So a phasor diagram shows the magnitude and phase angle of each phasor quantity in the complex number plane. So it shows the magnitude and phase angle in the complex number plane. So phase angles are measured counterclockwise from the positive level, real axis, and magnitudes are measured from the origin of the axis. Okay, so here we have x-axis, which is the real axis. This is the real axis. And this is the imaginary axis. Sometimes real axis is denoted as +1, and the imaginary axis is denoted as +g, So sometimes you will not see real axis, imaginary axis written, you will see +1 and +g. Okay, so the angles are measured from this axis, from the real axis. So we measure the positive angles. In this direction, clockwise direction, we measure the negative angles. And the magnitude will be measured from the origin, So let's start with this phasor. So this phasor is given as 10 into angle 30. So first of all, angle 30 is positive. So I need to measure positive angle in the counterclockwise direction, starting from the real axis. So here is the real axis, and now I measure in this direction 30 degrees. So here I have 30 degrees. So this angle is 30 degrees. And as you see, I measure it from the real axis in the counterclockwise direction because it is positive angle. And then I will draw a line starting from the origin at this 30 degrees angle, and the length of this line will be 10 units, because the magnitude here is 10. So for example, 10 centimeters, 10 inches, whatever scale you are using, So this length represents 10 units. And this angle, as you see, represents 30 degrees. So now I will draw another phasor, which is also with a positive angle. So here we have a 12, the magnitude is 12, and the angle is 150. And this 150 is positive. So I need to start from the real axis and to measure 150 degrees in the positive direction, which is in the counterclockwise direction. So I'm starting from this point and going up in the counterclockwise direction, and I'm measuring an angle of 150. And at this angle, I will draw a line, the length of which is 12 units, starting from the origin and with that length, which is 12 centimeters or whatever. So this will be 12 into 150 degrees. Is it clear, please, so far?
Yes.
Yes,
Okay.
it is.
Okay. Now I want to draw this phasor, which is 5 into angle -45. So 5 represents the length. So I know now that the length will be 5 centimeters, or whatever scale you have, 5 units. And the angle, I look at the angle. The angle here is -45. So I need to use a 45 degrees, but in the negative direction. And negative direction is the clockwise direction. So again, I will start measuring the angle from the real axis, but I will go with the clockwise direction and measure an angle 45 degrees. So this angle is 45 degrees. I started from the real axis in the clockwise direction. Why is that? Because it is -45. And then at this angle, starting from the origin, I will draw a line and or an arrow, and this arrow has 5 units of the length. So it could be 5 centimeters or whatever. And here, the last phasor in this example is 8 into -170. And again, once it is negative, I will start from the real axis in all cases. Once it is negative, I will go in the clockwise direction and I will measure an angle negative 170. 170. So this is negative 1 degrees. And from the origin at this angle, I will draw an arrow with 8 units of length. With 8 units of length. Is it clear so far, please?
Yes, it is.
Okay. So let's draw a phasor, let's say 8 units into an angle 190 degrees. So how it would be? Who can please dictate me so we can find this phasor? So is the angle positive or negative?
It's positive.
Positive. Okay, so I need to go in the clockwise direction or in the counterclockwise direction?
Counterclockwise.
Counterclockwise. So I need to measure 190 in the counterclockwise, right?
Yes.
So this is 90 up to here, and this is 180 up to here, and then I need to add 10 degrees more. So this is 10 degrees more. So this is the angle, sorry. So this is the angle, right?
Yes.
So this is the angle 190 degrees. Okay, and now I need to draw 8 unit length from the origin. So this is the origin, and this is 8 unit. So what we notice here? What we notice here?
It's the same as 8, and then the angle negative 170 degrees.
Yes, exactly. So each phasor can be represented with 2 angles in the complex plane. Either the angle which is measured in the counterclockwise direction and it will be positive, or the angle which is measured in the clockwise direction and it will be negative. So each phasor can be represented by 2 values. We engineers prefer to go with the least numbers. So here I have negative 170 and here I have 190. So 170 is less than 190. I will not consider the sign. I'm considering only the number. So 170 is less than 190. So I prefer to represent this phasor by this expression. But if you represent this phasor by this expression, it is correct and no one can say that it is correct. So you can do so, although we prefer to go with the small numbers. So, and this is also can be represented from the other side. This phasor can be represented from other side and so on. So each phasor can be represented using 2 angles. One angle measured in the clockwise direction, which will be negative, and another angle measured from the counterclockwise direction, and it will be positive. But we prefer to use the list numbers. Okay, any questions, please, about phasor diagram? Okay, so at this point, I will end this lecture. And so please, if you don't have any questions, so see you after tomorrow.
Professor, I have a question.
Go ahead, please.